with that, we can start with our web seminar today. I'm really pleased to have Mr. Kempf from FFT here today, and we will see an interesting presentation called FibreTec3D, 3D robot-based filament winding potentials, process, and applications. I think it's a cool, innovative new technology, and I'm really keen and looking forward to this presentation. Mr. Kempf, please go ahead. The stage is yours.
Thank you, Mr. Brenken, for the welcoming warm words. And also good morning to the audience. Ladies and gentlemen, welcome to FFT's presentation here at the Composites United Network. We are really pleased to be here, to be able to present you this topic. And we will start off with a short insight into the company. In the next 25 minutes, I will share with you the most recent addition and innovation to our portfolio, the advanced filament winding process called FibreTec3D. Mr. Brenken already mentioned the rough agenda. We will start off with a short insight into the process. We'll then be able to do some applications and use cases, and afterwards discuss the topic in a Q&A. In order to provide a proper background, I will start off with a short insight into our product and service range and how the carbon fiber solutions fit into that context of the company. Before starting with the presentation, I would actually like to introduce myself. My name is Nicolai Kempf. I'm 27 years old, started my career at FFT in 2015 for a corporate study program ending in 2018 with a bachelor's degree in virtual engineering, what is basically mechanical engineering with focus on computational applications like finite element and CFD. After a short internship at Porsche's R&D center in Weissach, I returned to FFT, went through various stations in project coordination, claim management, supporting body-in-white projects and proposals in Germany and in China before I recently joined our strategic sales department. With that, within that, I'm responsible for lightweight components, the related body shop concepts, and also selected OEM customers. As a part of the Fosun Group and core component of their intelligent manufacturing branch, FFT is a worldwide connected partner for manufacturing solutions. Since 1974, FFT has operated as a turnkey supplier for production systems with a strong focus mainly on the automotive industry in Germany. With increasing demand for automation, FFT expanded globally with subsidiaries in Europe, China, and North America in order to satisfy the customers' needs on the local markets. Besides our role as a system integrator, line builder, in the last 10 years, FFT has developed an in-depth expertise in the field of CFRP processing and applications, ranging from hand lamination, especially of tailor-made body-in-white fixtures, to fully automated CFRP braiding systems for the OEMs for car parts. Besides our core business as a turnkey line builder, we are also a product supplier for state-of-the-art joining equipment and a reliable partner for the aviation industry. What is of course also a driving factor regarding our know-how of CFRP applications. Closely linked with the before mentioned is our lightweight division, dealing with the coordination, realization, and the engineering for the CFRP products. And furthermore, with the transformation from conventional towards electric powertrains for cars, FFT also enhanced its portfolio with fuel cell production lines and highly flexible e-mobility solutions, such as turnkey battery assembly lines. And the last further integral component of a lean production nowadays is the use of IoT big data applications, which we develop in our digital innovation department together with our subsidiary EKS Intec. Originally, the process presented in the following slides was developed by Mercedes-Benz in their research and development department for assembly technologies, the so-called TechFabrik. Due to the broad variety of expertise in CFRP processing and applications, we as FFT were given the opportunity to be their partner for the industrialization and sales of the product. Both Mercedes-Benz and FFT have been looking for the same benefits, as well as they were encountering the same problems with lightweight components. And so do other people as well, as seen right here in the chart. These two show the pros and cons of lightweight components in clockwise ascending order. And as most of the benefits may be intuitive, like improved ergonomics, better operability of handling devices, energy savings, and increase of general productivity, the downsides might be a little bit more specific. The dependencies on special suppliers, missing repair concepts, as well as high R&D efforts seem to discourage companies from using lightweight design. But what if we can eliminate all these obstacles with different approaches? Let us consider the topic of missing demand on the market rather as a sum of the problems than part of the actual problems. So we can structure each of the points into product, process, and engineering related challenges. And then we will go on to target each of the points with a separate slide. So, let's talk about the topic, why do customers consider, for example, the issue of missing repair concepts and dependencies on special suppliers? Well, often their staff and maintenance are experienced with metal materials, but have only limited possibilities to deal with lightweight components, especially with composite materials. We see, for example, in the world of automotive production, that the duration of the repair is also a very driving factor for a product decision. And that these problems, which can be only tackled by adapting the product. It seems obvious that we can influence the manufacturing materials and material cost only by selecting the right processes and simplify these as much as possible. And if there are special requirements like mechanical and environmental properties, these are actually known before developing the product and are best to consider during the engineering and testing phase. And there is a good chance that if we can eliminate all of each of these single points, we can actually satisfy the customer's need and overcome that missing demand on the market. For sure, we all have an idea of the downsides of the manufacturing. Processes using carbon fiber fabrics require the semi-finished input material, as it's already related with higher costs for the resources to be processed. They usually also involve cutting waste, especially for complex three-dimensional geometries. And for some cases, this can amount up to 60% of the original fabric, what is critical regarding cost efficiency as well as the ecological aspect. Furthermore, processes like injection molding or LFI pure require a molding tool to define the geometry and are only reasonable in quantity, as the tooling is quite expensive and can reach up to 50,000 euros per square meter for metal, especially aluminum molds. Although there are highly automated processes, like for example, automated fiber placement, these usually require a predefined core to support the fabrics or fibers, or on the other hand, are restricted regarding output geometry of the final product, like applicable for pultrusion or braiding. To avoid these forementioned showstoppers, we are using a different approach. FibreTec3D. So what changes did we make? There is no use of carbon fiber fabric, but we use the fiber directly from the coil. Instead of producing waste by cutting and laminating the fabric, we use a very targeted and resource-efficient fiber impregnation. We don't use expensive tooling for the geometry definition, but we use simple and standardized aluminum mandrels for the geometry definition and as connection points. And to produce the components at the best cost and repetitive accuracy, we place the fiber with a robot. In the following video, you can see the filament winding process in action. The fiber is placed with a deposition tool, winded around the mandrels in order to generate the CFRP framework. The mandrels are also part of the final product, where other connectors, profiles, or sub-assemblies can be attached. After the process is finished, we store the profiles for hardening. This image right here shows our production system for the FibreTec parts. It consists of a turnable jig in the center for placement of these geometry defining mandrels seen in the video, and a robot on the right hand with the deposition tool for the fiber placement. Part of the system is also a pre-impregnation element for creating the matrix, or in other words, applying the resin hardener mixture onto the fiber. As the impregnation level has to be kept at a constant level and correct ratio during the process, we implemented a metering system visible at the top end of the jig. And as an alternative for the turnable jig, we can also use another robot with an attachment plate to manufacture complex 3D geometries, seen on the left hand of the production system. Here, this is another demo of our first series production system we saw on the slide before in the setup. Because of this, we use a double head, so we can scale up the process in general by a factor of 2. And the process you can see here is the cross winding as one of the various paths that we can apply with the robot. And what is, of course, one of the scenarios we are using to manufacture the here visible profiles during production. Before the fiber can be actually placed with the robot, as seen in the video, we have to fulfill a few other steps first in order to define the geometry and generate a process. Here you can see a schematic of what the design process looks like for a FibreTec3D component. We start with the definition of a design space and apply loads similar to other conventional numerical software solutions. Afterwards, a genetic algorithm generates a solution for the respective scenario and generates a geometry along the main load path. Then there is a defined fiber thickness, which is then the layout for the final product. And with that, a path generation tool generates the robot path within an offline programming process, what can be then extracted and uploaded into the robot for the commissioning of the system. To validate our product, testing is, of course, one of the crucial components. With our CFRP profiles, we went through a lot of testing already and are still ongoing. Starting with what can be seen on the left hand, qualitative experiments, through along the way testing to get an impression of the right direction. We also did some really detailed in-house testing, for example, for the deflection. As you can see in the image on the right hand, we tested our profiles with various different parameters. There were tests with fibers of different suppliers as well as different winding strategies. As the first use case for the profiles is device building for automotive production lines, our benchmark is nothing less than the industry standard profile made of aluminum. And the results are quite promising that we can reach, if not top, the bending properties and at the same time weighing only half as much. So far, we approached and streamlined the process, engineering and testing. But here's the question, how can we obtain a product that is easy to use as well as convenient for non-composite technicians, as it offers also enough design freedom? And the answer is not so hard. We use the Lego principle shown right here in the image. We manufacture a generic product that can be assembled by using a modular standard system, and therefore we wrote a design guideline that can be accessed by anyone to give some boundary conditions of the product's capabilities, and the final design is up to the imagination of the designing engineer. The image shows that the profiles can be easily connected to each other with conventional joining technologies, and the mandrels of the profiles are provided with an M6 thread, so standard screws can be used to assemble the construction. With different connectors, we have the possibility to realize angular designs as well as different distances between the profiles. Now, with that knowledge and idea, let us have another look at the barriers and risks section. And instantly we see that all the challenges we saw earlier are now solved. We have a convenient, easily to assemble and repair, standardized, automated, robot manufactured, and ecologically optimized product. And with that, our added value section suddenly becomes very easier accessible, and without any major downside, we cleared the way from benefiting from all the advantages and for all the lightweight applications that we can imagine. Now I will go on with a little bit more reality related things, so away from the process to the really approaches and applications we can obtain with the product. Let us get a little bit more specific. Regarding the manufacturing processes, we can, for example, achieve efficiency gains by replacing a steel or aluminum end-of-arm tooling with a carbon fiber-based one to reduce transfer times and availability, for example, of presses. Continuing in the body shop, carbon fiber tooling can and has already proven to flexibilize production systems by integrating more product variants into one production line. Due to the weight saving, a fully automated fixture change can be, for example, realized with the robots. It also puts us into the position, like seen in the video, to realize processes like on-the-fly welding, heavy payload handling, for example, for batteries or large underbodies of cars. But not only automated processes can be improved by the use of carbon fiber. Also, manual work can be conceptualized in a way more ergonomic manner than before. Examples are handling devices, templates, trolleys, mounting fixtures, and so on that can be shown later on in the presentation. For vehicle manufacturers, the benefits, of course, can be transferred into the product. With higher stiffness and less weight, this leads to better driving dynamics, reduction of emissions, and less downtime for charging cycles. By using CFRP components in logistics processes, these can be streamlined as energy demand and also total cost of ownership, as well as CO2 emissions are reduced, as later shown as a part of the reference projects. Let us have a look at another real-world problem. So in this image, you can see a comparison between our FibreTec profile and the aluminum counterpart. Besides the actual weight saving of 41% compared to the alu profile, we have various other mechanical advantages compared to it. As we have a lateral detachment of the aluminum connectors, there is an optimized flux of force. Compared to the alu profiles, we also have a reduced complexity of the connectors due to the flat design, what allows us to water cut them. As our connectors are made of high-strength aluminum compared to the lower material quality of the casted aluminum connectors of the competitor product, we can obtain a higher stiffness at similar weight. The mandrels are also provided, already mentioned, with threads at delivery, what accelerates the assembly process. Depending on the use case, we can achieve weight reductions for the overall gripper of up to 30%, depending on the layout of the handled part. Here you can see a sidewall gripper where a re-engineering was done and where we were able to get the weight of the overall system down by 16%. Related to the frame itself, we saved more than 28% without major design changes, but only replacing the aluminum profile with our FibreTec3D profiles. But the weight reduction is not the only positive aspect of such a gripper. Beneath the 16% reduction, for example, also for this underbody gripper shown here in the image on the bottom right, we can also enable efficiency gains and reduction of emissions. Tests have shown that the downsizing of a robot can lead to energy savings as large as 50%, and the resulting cost effect could pass the 15,000 euro mark. And please mind that these numbers were forecasted before the massive increase of energy prices. Beneath that environmental or production-related cost savings, we also can gain a reduced system invest up to 5% seen on a single robot gripper combination. Another example is the optimization of this special load carrier. In 2022, we received the task to optimize this carrier, and the input steel construction, which we re-engineered, weighs around 400 kilos. With that weight, a number of 25 carriers, including parts, would be the limit to be carried on a truck. In order to get a better cross-tear ratio, we designed a FibreTec carrier that was 90 kilos lighter while fulfilling the same mechanical requirements. There were 4 carriers to be stacked onto each other, and there were various other criteria that had to be met, like fatigue strength, various load cases, the results looked very promising, and tensions as well as displacement were in a feasible range for the series production. And to get another step further, we designed an even more optimized version of this carrier. Able to get the weight down by nearly the half. Further use cases I just mentioned are the use of ergonomical improvements and assembly and logistics applications. Therefore, for example, installation aids and mounting fixtures improve and can enable one-man processes where they were not possible before. For example, the devices for the cockpit adjustment, like seen here in the presentation, or the partition wall assembly for cars, as shown on the top right. For the transportation of product parts and components, transport trolleys handling devices or AGV carriers reduce weight and ease the material handling and logistics, and therefore also open new possibilities. As you can see, the highly automated CFRP technology FibreTec3D is just at the beginning, and we are still generating new examples and new potentials where we can see a use case, and that there are many possibilities also that we do not even think about at the moment. So we are looking forward really to discuss the ideas with you and develop therefore a lighter future. In the end, I am really thankful for the opportunity right here at the Composites United network, and therefore would like to close my presentation and open the Q&A session now together with you, get into the discussion and in contact. And also thank you, Mr. Branken, for letting us have this opportunity.
Yes, sure. Thank you very much for this interesting presentation, Mr. Kempf. It was, I think, a great and interesting talk.
I hope so.